Hey everyone, welcome to Linux Troubleshooting series. In this video, we are going to explore a real-world problem that confuses even the experienced engineers. So, when your app becomes slow or starts timing out, but CPU, memory, and disk all look normal. So, in this video, we'll recreate this problem, dig into what's happening under the hood, and learn how Linux file descriptors, the tiny handles to every open file or socket, can bring your app to a crawl when misused or exhausted. So by end of this module, you'll not just know how to fix the issue, you'll understand exactly why it happens. Alright, so here's what we are going to cover in this module. So we'll start with a real world scenario, a slow application that looks perfectly healthy from every angle. Then we'll dive into what's actually happening under the hood. We'll talk about file descriptors, what they are and why Linux limits them for every process. Once we understand the concept, we'll simulate the problem ourselves, intentionally exhaust file descriptors and watch how the system behaves when it runs out. After that, we'll go hands-on with Linux tools like lsof, strace and /proc to detect and confirm the issue. Finally, we'll look at how to fix it, how to prevent it from coming back, and what this troubleshooting process looks like in real-world production systems. So imagine this, you are an on-call engineer. Everything is looking fine, CPU usage is low, memory is stable, no IO spikes. Yet users are screaming that the app is painfully slow. You open the terminal, type in the top command, also glance at the htop command. Nothing looks alarming. It's one of those days where you feel something is wrong, but the metrics don't show it. This is exactly where many Linux performance issues hide. Not in CPU or memory, but in how your application interacts with the kernel. So today we will explore one of those invisible bottlenecks, the file descriptors. So before we move on and troubleshoot the issue that is of file descriptor exhaustion, it is very important for us to understand what file descriptors are in Linux. So in Linux, every process keeps track of the files and devices it's using through file descriptors. Just small integers like 0, 1 and 2. These numbers live in a table that's private to each process. So fd0 is standard input, fd1 is standard output and fd2 is standard error. Under the hood, those FDs point to entries in a system-wide file table, which hold things like file offset and open mode. Each entry then points to an inode, the file's metadata in the file system, and that inode points to actual data blocks on disk. So when a process reads or writes, it's really following this chain, that is file descriptor, file table, inode and data blocks. And that's how Linux knows exactly which file or device you are talking to. So moving on, when a process like a shell, a web browser, a web server or even a sleep starts running, the kernel automatically gives it three file descriptors, that is 0, 1 and 2. So 0 is standard input, the input string. So the keyboard is a input source. So the std input will be getting a 0 as file descriptor. 1 will be std standard output, that is output stream, a screen for an example or a console. 2 is for standard error, an error stream, a screen or console like a error, that will be your standard error. And then moving on, starting from 3, it will be allotted for open file sockets or pipes. So let's break down what this actually means. So for example, whenever a process opens a file, say a text file, a network socket, or even a dev null, the kernel doesn't hand the program a file name or path. Instead, it returns small integers like 3, 4, or 5. So now you will be having a question in your mind like why the numbers start from 0. So the kernel reserves the first three file descriptors for standard input output. So as we just saw, 0 will be standard input, 1 will be standard output, where the process writes the normal output, standard error, where the process writes a error. So even if your program doesn't open any file explicitly, these three file descriptors are always there. So every process that starts get these file descriptors that is 0, 1, 2 by default. All right, let's see file descriptors in action. First I'll show you the terminal device that this shell is connected to. I'll run this command, that is tty. So this prints /dev pts 0. That means this terminal session is using sudo terminal number 0. Now let's start a background process using the sleep command. So that is sleep 1000 with a ampersand. So this creates a new process and it inherits the file descriptors from this terminal. So fd0, fd1 and fd2, that is standard in, standard out and standard error, are all pointing to dev pts 0. To verify that, let's run the lsof command, that is list of open files. We will give the process ID that we just got here. Here it is. So there you can clearly see 0u, 1u and 2u pointing to dev pts 0, that is the tty that we got. So every terminal gets this. We'll also see when you open a new terminal, what will be the PTS for that terminal. So these are standard file descriptors, that is input, output and error, which every process gets by default. So now let's open another terminal and run tty over here. So here you can see dev pts 1. For the previous one, we got dev pts 0. So here, now again, let's run a sleep command. Again, the same one. Sleep 1000 with ampersand to run it in background. So here again we got another process ID. So let's see for that, list of open files -p for process and the ID 349769. Here again the same process. Dev pts1, it has three file descriptors, that is standard in, standard out and standard error. Now let's observe what happens when we redirect the output. We will be still in the PTS1, that is this terminal, and do a redirect. So there will be slightly modification, that is sleep 1000. We will redirect this time out.txt with a ampersand to run it in background. So here again we got a process ID. Let's do ls of, that is list of open files for that. So that is list ls of -p and the process ID. So here you can see fd0 and fd2 still pointing to dev pts1. Here it is. But there is a slight difference compared to this output. It has this one, which is pointing to out.txt. So what's happening behind the scene? The shell checks the fd1 is available. It replaces it with a file. The kernel gives the process its own file descriptor table, and the process continues running with fd1 pointing to the file. Now I think what we saw in the previous section will come back, and you will be able to recall what we discussed in the previous section, where we saw the table and on the inode table, the file descriptor table. So this is how Unix uses simple integers to represent open files, sockets, terminals, pipes, and devices. So now you must be wondering, and you might have a question, that why FD2, that is standard error,
still show up in lsof, even when there is no error. So it is obvious, right? It will naturally come to your mind like we haven't done anything related to error. Why the file descriptor of error, that is standard error, that is 2, still shows up. So file descriptor appearing in lsof does not mean it is being used. It only means it is open and available. So going by the analogy, just like how a room having a door doesn't mean someone is walking through it, it just means the door exists, right? So consider it that way. So every Unix process starts with these three file descriptors that we saw. So in our lsof output, that is, for example, sleep, what all these mean. So every two here, as you can see, exist. It's pointing to a terminal that is dev pts1. The program can write errors there. The program did not necessarily write errors. So FD2, that is for standard error, shows up not because it printed an error, but because every process must have standard error open. So why does standard error point to the terminal? Because if a program crashes or prints an error, the user should see it immediately. Imagine stdout is redirected to a file. Standard error still goes to the terminal.
Yes, so now we have just created a simple demo script wherein we'll show how the file descriptors get allotted when a file is opened, when a file is closed, and again, after closing the file that got closed, how the file descriptor that was allotted to that file gets released, and the new file that comes up can take it up, which was released. So let's start with it. So first we'll just go through what exactly the script is. That is, first I have just created a script wherein the process ID will be printed. So you can grab that process ID and do a list of open files on that process ID and see how the file descriptors are getting allotted and then getting released. So f1 is equal to open, we are opening a file1.txt. Then we are opening a file2.txt where f2 is equal to open file2.txt with write operation. Then we are closing the file 1, that is file1.txt gets closed. And here we will be able to see how the file descriptor that was allotted to file 1 would be getting released. After that, we'll just add 2-3 lines of code wherein we'll open a file3.txt and see how the file descriptor that was released for file 1 gets allotted to the file 3 that was opened. So here it is, and let's go ahead. So we'll just do Python 3 fd.demo.py. So here it has printed out the process ID, that is 85645. This we can grab and open it in another terminal and do a watch on the list of open files with the process ID. Here we are doing a watch on a list of open files and see how the file descriptors are getting allotted. So at present there are no files being opened as we have just we have just started the Python script and a process ID is only given. So at this point, we are just seeing the three default descriptors, that is std input, standard output, and standard error. They are 0, 1, and 2, as you can see here. Now what we'll do is we'll open a file. So here it is. So a file1.txt is opened. So we'll expect fd3 that is after the default file descriptors being allotted, and here it is. We are getting the file descriptor 3 that is allotted to file1.txt, which is open. Now we'll open another file2.txt. Now we'll expect file descriptor 4 to be allotted to this one. So yeah, here it is. So now what we'll do is we'll try to close the file1.txt, which is there in the script. So next it says press enter to close the first file. Yeah. So the file1.txt is closed. Now what we'll expect is we'll expect file1.txt that had a descriptor number 3 being released. So yes, so 3 is released, 4 is still there because file 2 is still open. Now what we'll do is we'll come out of this.
and add a line of code wherein we will say f3 is equal to open file3.txt with a write operation, and we'll print out that as well just for our understanding. It is file3.txt. Okay, before this, we'll just add an input so it becomes a bit clear. Input. That is it. So let's see that in action. So again, we will run that file, that is Python script. So here we got a process ID of 87775. We'll do a watch again. Yeah, so you can see the 3 default descriptors being allotted to this program. We'll open a file. We opened a file with file1, which got the file descriptor number 3 allotted. Now we'll open another file. We got file2 being allotted, descriptor number 4. Now what we'll do is close the file1. So you can see the third one being released. So when it is released, when we are opening a file3, we'll expect file descriptor 3 being allotted to that one, as it has been already released for file1. So here it is. So we will open file3 and we can see the third number file descriptor which was released for file1 got allotted to file descriptor 3 got allotted to file3. So this way we understood how the file descriptors are used, and opening and closing is also an important part which we'll understand going forward. And in next section we'll get to know what this file descriptor exhaustion is and how it happened and how we should avoid it. So let's go ahead. So now let's get back to the scenario that we just started in the beginning, wherein you are getting complaints from your developers or the users of your application that the application is slowing down or the application is not responding. So sometimes your application slows down or starts timing out. So now when you log into the system and see the CPU and memory, it totally looks fine. So you check top and everything looks calm. So what's going on? So now we will try to simulate this scenario, how this will be happening in a production environment. So let's go about it. So what I've done is I've created two scripts. One is the file descriptor exhaustion script, and a script wherein we fix the issue that the leaky script or the file descriptor exhaustion script is doing. So before moving this, understand what the ulimit -n command that is on your screen shows you. So every open file, socket or pipe in Linux is represented by a small integer, a file descriptor. So they live in the kernel's file table, and every process gets its own table of FDs. To prevent a single process from consuming all system resources, Linux enforces limits, both per process and system-wide. So you can check your current per process limit using this command, that is ulimit -n. Ulimit -n. So yeah, so current limit is 102 per process. This shows that maximum number of file descriptor your current shell and any process it starts can open. For example, if I run ulimit -n and now I'm seeing 1024, it means my application can open up to 1024 files or socket before hitting an error. So this is a limit. You can also change it to whatever you like, but it is always preferred to keep it the default, that is 1024, or not lowering it, or else your file descriptor exhaustion will happen. So now what we'll do is we'll just run a simple Python server. It will listen on port 8080 and handles incoming request using threads. But this script that we will be running will have a bug. It accepts connection, handles them, and never closes the sockets. So as we learned in previous section, it is important for the program or the application to close the files. So the other file, for example, file pipe or socket opens up, it can use that one, the one that is freed up. So if it fails to close, the problem will occur and your file descriptor exhaustion will happen. So I'll just start the server. So I'll share these scripts in a GitHub repo so you can try it at your uh, own local system as well. So here we have the ulimit as 1024. So I'll run the leak.py Python file which has the bug that is that will cause file descriptor exhaustion issue. So now I will run the leaky one that will cause the file descriptor thing. Python 3 and we will run it in background. So it is listening on port 8080. Good. So now what we will do is we will do a list of open files on the process that it is the process ID. For example, 34360 is the process ID which we saw over here. So now it will give you a list of open files. And before that, let's see how the file descriptor table or the number of things that it has occupied. Let's see how it is opening. So now it is only having one file descriptor that is 3 that is being allotted. Now let's run few requests on this. Like let's do curl. So we'll do a curl of 1 to 1000 request on this Python server. Okay, now let's see. Okay, it just exited, right? So it has exited after going to 974. And it might have the application might have also gone down, which is what we are looking for. So let's see if the application is there. It is still there, it seems. Now what we'll do is on the other terminal we'll do a strace. So strace and the process ID, that is the process ID is 34360. And let's see what the strace has to say. Okay. So now it is listening and strace will give us a good understanding of what is happening. So now if you see, it is free and top is also fine. But as we saw, some requests are timing out, right? We saw in our previous thing. So let's do, and one more thing that we can do is we can also go and check the number of files that are open. You can also see the open files that are there. So let's just put the process ID. So every process is a file. So we'll just grab the process ID and see over here. So open files are 1024. So now again let's run a command and we will also see the strace that will happen for this. So yeah, so I think strace also exited. I think the application also exited, and you will have to go through the strace what is happening. It exited. Let's see why it exited through the trace. So if you go through the trace, we are just getting closer to, yeah. So here it started giving you too many open files. This is a result of the file descriptor exhaustion. So here the number of file descriptors that are there of 1024, it has exceeded that, and your files are taken up. The file descriptor that are there are taken up and no more can be allotted. So this is the reason that we found out that how the file descriptor issue was found. We found out that through strace. In the trace we saw that you can see too many open files is been, and it is for leak.py, the Python script that we just ran. So now we have understood what file descriptor issue is and how to troubleshoot it and find out the program that is giving you the too many open files issue. So here you can easily see the leak.py is the culprit over here. So now we identified the issue. What about the fix? Now the application is leaking and the file descriptors or the files are not getting closed, due to which the file descriptors allotted are getting exhausted. So how do you go about fixing it? So for that we'll just run a similar Python server, but this time we'll apply the fix to the code and run it again, and we'll see how the files are open and how they are closed and the file descriptor exhaustion issue is fixed. So let's see. So we have a simple Python script that is fd underscore fixed. So here what we are doing, most important thing is close the connection when done. This piece of code is the one that we'll be applying. So this will solve the issue. Before this, the code that was buggy didn't have this in that. So the files that were open were not closing. So we'll just start the server. Let's again see if there is any running on 8080. There is no application running on 8080. So let's run it. Python 3 every, and we'll do a and. So it's listening on port 8080. We'll again see what is the ulimit. Ulimit is 1024. And now let's go on and send request, or we'll do a 1000 request. So the requests are going through. So let's also run an strace. Before that, we'll just see the, so we are getting it. So we'll also do a check 37425. So now we can see there is only 15 file, the count is 15, and you might also see there are no file descriptors that are unnecessarily hogging. So let's run again a set of request and also see the strace. So strace is not showing any signs of list of open files or the error that we saw before, that files, too many open files issue. So here the processes are running concurrently, but they are also closing it. Because of that, we are not seeing any issues related to file descriptor exhaustion. So let's run it again. We'll just give it one more. See, the strace is showing no signs of too many open files or such errors that we saw before, right? So I think we have fixed the issue through a simple line of code. So this is a simulation that we did. There might be a bigger issue that you might face related to file descriptor exhaustion, but the steps that we carried out will be same. So whenever you feel like there is a issue related to file descriptor exhaustion, you can first go to your, first you can see the limit that is there. So doing ulimit -n, you will get to know what the limit is. After that, you can just go through the lsof that we did, list of open files. So for, and put your process ID over here, and you get to see if the file descriptors are adding up. If they are not adding up, you will not see a list that is going through over here. In the last issue that we had, the list was just coming and it was just adding up to the number of rows that this output had, right? So here it is not adding up. Even if we are sending a request concurrently, it is closing out. So this command will also give you a good idea what is happening to your file descriptor thing. Also, one more command that we saw was the proc in the proc file system. So doing a cat of proc and the process ID, that is 37425, and limits. So here it gives you max open files, soft limit and hard limit, right? So this also gives you a good idea what your process is doing. And then we of course had strace, which gave us a good understanding of what was, what the issue was in the previous leaky code, right? It showed up too many open files error. So from that you got to understand that the code itself is buggy and you need to fix that. So what we learned from all these demos and the slides that we went through before. So we learned about file descriptors. So in Linux, every file, socket or pipe a process opens gets a file descriptor, basically a small number that represents that open resource. Each process has a limit visible using ulimit -n. So if it runs out, new connections or file can't open, leading to errors like too many open files. So using ulimit -n, we found out the limit that is set for the number of file descriptors a process can take. Then we simulated the issue. We built a small Python server that forgets to close client connections. Over time, the number of open file descriptors keeps increasing. How you watch or how you find that out? Using list of open files -p, the process ID, and the count. So if everything looks normal, CPU memory, but the app becomes unresponsive, you know what to do. After that, we went through the rabbit hole and found out the troubleshooting approach was running strace. We learned about the strace command. You do a strace -p and the process ID. It, if it shows repeated, accept function calls but no close calls, that's the giveaway, a file descriptor leak. So we found out there was a message in the log, right? There are too many open files. So using a strace, we found that out. What was the fix? The fix, always close your connections. Once you find it out through strace, you go through the code or you tell the developers that the code is buggy and is leaking. If you truly need more connections, raise the limit safely using etc security limits.conf. But that's not the fix, right? You need to fix the leaky or buggy code. So the takeaway that I'll take from this entire session is you should always remember not all slowness is CPU or memory related. Sometimes your app just forgot to close a few too many files can also get your system to a standstill.